This video is about Thyristor commutation techniques. In the previous video, we have seen various triggering methods to turn on a thyristor. Similarly, the techniques used to turn off a thyristor are called thyristor commutation techniques. For triggering a thyristor should be taken from the state of forward blocking state to the forward conduction state, right? Then obviously, thyristor commutation means bringing the thyristor back into the forward blocking state from the forward conduction state. For this purpose, we have to reduce the forward current below the holding current level. We have two techniques for commutation. The first one is natural commutation, the second one is forced commutation. Natural commutation means the commutation that should occur naturally. The figure shown here represents the natural commutation. You can observe this is just a normal thyristor circuit with AC supply and the load. There is no any external circuit to make the thyristor off. We know that in an AC signal, when a positive cycle reaches to zero, means during a negative cycle, the anode current becomes zero and a reverse voltage is applied across the thyristor. So the thyristor goes into the off state. This happens naturally during the negative half cycle of the AC supply. So please note that the natural commutation occurs only in AC circuits. Next type of commutation is the forced commutation. The forced commutation is required in DC circuits because there is no natural zero current in DC circuits. That is why the forced commutation is also called as DC commutation. And because it does not occur naturally, it requires an external circuit containing elements like inductance, capacitance to reduce the anode current below the holding current value. Forced commutation is classified into five categories: Class A, Class B, Class C, Class D, and Class E. The first type of forced commutation is the Class A commutation or self or load commutation. The figure shown here represents the self or load commutation. The combination of inductor, capacitor, and load resistor used in the circuit forms a second order underdamped circuit, which gives a brief idea that this circuit helps in switching the thyristor off. Supplying the input voltage to this circuit will not turn on the thyristor because it requires a gate pulse to get turned on. Now, when the thyristor turns on with the gate pulse, the current starts flowing through the inductor and the capacitor charges to the peak value of the input voltage. Inductor also builds a magnetic field and stores energy when current passes through it. Now, after the capacitor gets fully charged to the peak value of the input voltage, there is no potential difference in the circuit to make the current to flow continuously. So the current starts decreasing. But we know that the inductor opposes the sudden changes in current. The current, which was actually increasing, undergoes a sudden decrease because the capacitor gets fully charged. This sudden change in current is not allowed by the inductor. So, inductor tries to make this decrease in current gradual, not sudden. To do this, a voltage is induced across the inductor according to Lenz's law in opposite polarity. Because of the inductor reversed polarity, the current is allowed to decrease but gradually. And when this current reaches to a value lesser than the holding current value, then the thyristor gets turned off. So, this is the way in which the thyristor gets turned off in Class A commutation. And note that this Class A commutation is the most used technique among all the thyristor commutation techniques. Next type of forced commutation is the Class B commutation or resonant pulse commutation. The figure shows the Class B commutation circuit, and you can observe an LC resonant circuit is connected in parallel. Note the difference between Class B and Class A commutation circuits. In Class A commutation, the capacitor charges up to the peak value of the input voltage only when the thyristor gets on. But in class B commutation circuit, the capacitor need not wait until the thyristor gets turned on. With the DC supply voltage, the capacitor starts charging and the capacitor charges up to the input voltage Vs. When capacitor charges up to the peak value of the input voltage, capacitor holds a voltage that opposes conduction and the thyristor remains in the off state. To make the thyristor on, the gate pulse needs to be applied. With the gate pulse, the thyristor gets turned on. We know that inductor provides steady flow of current because it does not allow sudden changes in current. But here we can find there is a combination of inductor and capacitor which forms a resonant circuit. Because of the presence of the resonant circuit, at resonance, the circuit starts oscillating. So the current that flows through this LC branch is also an oscillating one, which means the current flowing through this LC branch is a sinusoidal current. Note that when the thyristor gets turned on with the gate pulse, the capacitor which was initially charged discharges the entire voltage. And note that when the capacitor was charging initially, when thyristor is not turned on, inductor also must have stored the energy. This stored energy of the inductor produces an oscillating current at resonance. Now the capacitor starts charging again in the reverse polarity because of this sinusoidal current. Now when the capacitor is charged to the reverse polarity, this reverse voltage appears across the thyristor. This reverse voltage opposes the forward conduction of the thyristor by producing a current which is in the opposite direction to the anode current. So this counteracting current will reduce the anode current to the level of less than holding current, making the thyristor off. In this way, the thyristor is turned off using class B commutation. Next type of thyristor commutation is class C commutation or complementary commutation. The figure represents the class C commutation where you can observe there are two thyristors in parallel. One is the main thyristor T1 and the thyristor T2 is the auxiliary thyristor. Initially, when no gate pulse is applied, both the thyristors will be in the off state and the capacitor remains in the uncharged state. When a gate pulse is applied to thyristor T1, T1 gets turned on and there are two paths for the current. One is through R1 and T1 and the other path is through R2 capacitor and T1. With the current flow in the second path R2C and T1, the capacitor gets charged. And note that the capacitor charges to the value of the input voltage with plate B positive and plate A negative. Now, when a gate pulse is applied to thyristor T2 gets turned on. Now, a new current path is created through C and T2. So, the capacitor discharges through T2 and so a reverse voltage appears across the thyristor T1. This forces the thyristor T1 to turn off. But then the capacitor with the path R1C T2, the capacitor starts charging again with the reverse polarity with plate A positive and plate B negative. So now when we turn on T1 with gate pulse, again the capacitor discharges through T1 and turns the thyristor T2 off. In this way, when one thyristor becomes on, it is forcing the other thyristor to become off. So that is why this commutation is known as complementary commutation. In this way, in complementary commutation, the main thyristor T1 is turned off. The next type of forced commutation is the class D commutation or impulse commutation. It is also called as voltage commutation. The circuit shown here represents the impulse commutation in which again there are two thyristors, the main thyristor T1 and the auxiliary thyristor T2. When no gate pulse is applied to thyristors T1 and T2, both are in the off state and the capacitor remains in the uncharged state because there is no current flow in the circuit. With the gate pulse at T1, the thyristor T1 gets turned on. So the load current starts flowing through the thyristor T1. Now the capacitor starts charging through the inductor and diode with plate B positive and plate A negative. The reason why the capacitor chooses this way to get charged is that inductor allows the smoother current flow and the diode also ensures the current flow is unidirectional. Now, when we apply a gate pulse to T2, the thyristor T2 gets turned on. When T2 is on, the capacitor starts discharging through T2 and a reverse voltage gets applied across T1, making the thyristor T1 off. When capacitor discharges through the thyristor T2, a high surge current is created, but this high surge current is not allowed by the inductor L, and the inductor opposes the sudden change in current by developing a back EMF across the inductor L. This back EMF is generated because the inductor uses its magnetic energy stored in it. When the capacitor is discharging through the thyristor T2 suddenly, but the inductor does not take this sudden change in current, it builds up its energy gradually. So, this magnetic energy is used in developing the back EMF across the inductor. This back EMF produces a current in the direction opposite to the discharging current, and this makes the capacitor to charge again with plate A positive and plate B negative. Now, once the capacitor is fully charged, it does not allow DC current to flow. So, because of no current through the thyristor T2, the thyristor T2 gets automatically off and T1 is also off. And now one cycle is completed. To start the next cycle, again thyristor T1 should get a gate pulse. In this way, the commutation is done in class D commutation. Next type of commutation is class E commutation or external pulse commutation. This is the circuit diagram of class E commutation. You can observe a pulse transformer circuit is used to turn off the thyristor. When the gate pulse is given, the thyristor gets turned on. So, the anode current IA flows. Now, the pulse transformer generates a pulse and this pulse is given to the thyristor circuit. So, an opposite current IP flows through the thyristor circuit. And this opposite current IP opposes the flow of the anode current, and when the difference between the anode current and the opposite current becomes less than holding current value, then the thyristor will get turned off. And you can observe there is a capacitor in the circuit. The capacitor is used to prevent the accidental triggering that triggers when an unintentional high voltage appears across the thyristor gets turned on accidentally. So, to prevent accidental triggering, a capacitor is placed across the thyristor because we know that capacitor opposes the sudden change of voltages. So, the capacitor is used for dV by dt protection of the thyristor. In this way, the thyristor is turned off in external pulse commutation. This concludes the topic of commutation techniques for a thyristor. If you like the video, kindly subscribe to my channel and like and share the video. Kindly help me to help you.